Welcome to the 12th lecture of the Fluid Machinery course. In this lecture, we will discuss what is specific speed, what is its significance, and how to derive an expression for specific speed and a numerical problem related to the specific speed. And this is in fact from module 2. What do you mean by specific speed of a turbine? It is a very important parameter used in the performance analysis of hydraulic turbines and even hydraulic pumps. And the related question is define the specific speed of a turbine, explain the significance of specific speed. So what exactly is specific speed? Specific speed of a given turbine is the speed of an imaginary turbine geometrically similar to the given one, which would develop unit shaft power, that is 1 kilowatt power, under a net head of 1 meter. So that means the specific speed of a particular turbine is the speed of an imaginary turbine geometrically similar to the given one and which develops 1 kilowatt shaft power while working under a head of 1 meter. The mathematical expression for the specific speed is given by, it is denoted by n suffix s, that is equal to n root of p divided by h raised to 5 by 4, where n is the rotational speed of the runner in RPM and p is the shaft power in kilowatts. Remember, if you want to get the specific speed in SI units, then the power must be substituted in kilowatts. And if you want the specific speed in metric units, then the power must be substituted in horsepower, that is HP. Better we use the specific speed in SI units, where the shaft power P is required to be substituted in kilowatts. The net head H must be in meters. Now the ranges of specific speed. When we calculate the specific speed in SI units for the different type of or for the different category of turbines, so what we can find is the Pelton turbines. Those are impulse turbines which will have the specific speed range between 8.5 and 50. So if you have a Pelton turbine with single jet, then its specific speed will be between 8.5 to 30. And if you have a Pelton turbine with multiple jets, that's more than one jet, say up to 6 jets, you can have the specific speed ranging from 30 to 50. For Francis turbines, the specific speed range is from 50 to 250. That means radial flow reaction turbines will be having the specific speed range from 50 to 250 when the specific speed is expressed in SI units. Then Kaplan turbines, which are axial flow reaction turbines, which will have the specific speed in the range of 250 to 860. Remember, these ranges are applicable when the specific speed is expressed in SI units, and in the expression the power must be in kilowatts. Now what is the significance of this specific speed? The specific speed is used in the selection criteria. That is, it is used in the selection of turbines for a particular application. It is also used to assess the performance characteristics of the turbines. It can also be used to identify the category of turbines, that is, in which homologous series does the given turbine belong to. Turbines which have common characteristics or which are geometrically similar are grouped in the same family called homologous series. The turbines from the same homologous series will have common characteristics. It is important to note that the high head turbines will have lower ranges of specific speed, and medium head and medium discharge turbines will have medium range of specific speed, like reaction turbines, like Francis turbines, which are of course radial flow reaction turbines, medium discharge, medium head and medium specific speed range. Whereas Pelton turbines or impulse turbines, they will be high head turbines and low discharge and low specific speed. And on the other hand, Kaplan turbines, they are axial flow reaction turbines. They have very low head and they have very high, in fact the largest flow rates, and they have high specific speed range also. Now let us proceed and derive an expression for the specific speed of a turbine. So the related exam question is, derive an expression for the specific speed. What is the significance of type number in turbines? So we will start from the tangential or peripheral velocity of the runner. We know that the tangential or peripheral velocity of the runner is given by u is equal to pi dn by 60, where d is the diameter of the runner and n is the rotational speed of the runner in rpm. In this relation, pi and 60 are constants. So we can convert this equality into proportionality. So u is proportional to dn. So u is proportional to the product of diameter and the rotational speed n. Let it be equation number 1. Now consider the speed ratio of the turbine, denoted by k suffix u, that is equal to u divided by root of 2gh, where h is the net head, and u is equal to ku into root of 2gh. Ku and the gravitational acceleration g are constants. Therefore, you can write the proportionality of u in this case as u is proportional to a root of h, because k into root of ku into root of 2g, that part is constant. So u is proportional to root of h. Now we got two expressions for u. The first one is u is proportional to dn, and the second one u is proportional to root of h. That is equation 2. So from 1 and 2, you can write dn is proportional to root of h. That means d is proportional to root of h divided by n, taking n to the other side. So d is proportional to root of h by n. Let it be equation number 3. Now consider the flow ratio given by k suffix f is equal to velocity of flow Vf divided by root of 2gh. What is Vf? Vf is equal to kf into root of 2gh. In this expression for Vf, kf and root of 2g are constants. So we can write Vf is proportional to a root of h. Let it be equation number 4. Now consider the expression for discharge applicable for Francis turbines. You can make use of the discharge expression for any other turbine, but the result will be the same, but the modifications will be different. It is easy for us to consider the discharge expression of the Francis turbine. So the discharge Q is equal to pi dB into Vf, that is flow area multiplied by flow velocity, where the d is the diameter of the runner and b is the breadth or width of the runner. Vf is the flow component of velocity. So Q is now proportional to dB Vf, because pi is constant. So Q is proportional to the product of the diameter, breadth of the runner and the velocity of flow. Now the connection between the diameter of the runner and width of the runner. We know that the breadth of the runner is proportional to the diameter. So you can replace the breadth by the diameter. Remember, it is not equality, it is proportionality. So B is proportional to D. Therefore, in this expression for the discharge, in that proportion, I am going to replace the breadth or width of the runner by the diameter. So Q is proportional to D into, instead of breadth we have again diameter, so therefore diameter square it will become into Vf. So Q is proportional to D square into Vf. Let it be equation number 5. Now we got an expression for the discharge in which we have the diameter of the runner and the flow component of velocity. See, already from equation 3 we got the proportionality for the diameter, and from equation 4 we have the proportionality for Vf. So now substitute 3 and 4 in equation 5. So Q is proportional to, instead of diameter I am going to substitute root of h by n. So D square, that is root of h by n square, then into Vf. Instead of Vf we will substitute root of h. So therefore Q is proportional to root of h by n whole square into root of h. So what do you get? Root of h square is h into root of h divided by n square. So Q is proportional to h root of h by n square. That is h into root of h means h raised to 1 by 2. So h raised to 1 into h raised to 1 by 2, that is h raised to 1 plus 1 by 2, that is h raised to 3 by 2. So Q is proportional to h raised to 3 by 2 divided by n square. Let it be equation number 6. This is the expression for the discharge in terms of head and the speed. Ultimately what we need to get is, we have to introduce power into the expression, and we need to get an expression which contains the proportionality of shaft power with the net head and the speed. For that purpose we will consider the overall efficiency. See, the overall efficiency eta naught is equal to shaft power by water power, that is eta naught is equal to P by rho Q GH. So what is shaft power P? P is equal to overall efficiency eta naught into rho Q GH, in which eta naught, rho and G are constants. So when you convert this into a proportionality, so you will get P is proportional to Q and H. Q and H are the variables. Now we already got an expression for the discharge in terms of head and the speed. From equation 6 you can substitute that in the current one, which is P is proportional to QH. Let it be equation number 7. So substitute the value of Q or proportionality of Q from equation 6 in the proportionality expression for power. So therefore P is proportional to, what is Q? Q is h raised to 3 by 2 by n square, then into h, because P is proportional to Q into h. So P is proportional to, now instead of Q, h raised to 3 by 2 by n square, then into h. If we simplify that, now P is proportional to h raised to 3 by 2 into h raised to 1 divided by n square. Now h raised to 3 by 2 into h raised to 1, that is h raised to 3 by 2 plus 1. The indices can be added, that is h raised to 5 by 2. So P is proportional to h raised to 5 by 2 divided by n square. This is a relation we were searching for, because now we got shaft power in terms of head and the speed. So now you convert this proportionality into an equality by introducing a constant. Let that constant be K. Therefore shaft power P is equal to a constant K into h raised to 5 by 2 divided by n square. Let it be equation number 8. Now we have to get the value of this constant K from the definition of specific speed. That is, specific speed is the speed of an imaginary turbine geometrically similar to the given one, which would develop 1 kilowatt when working under a head of 1 meter. So when n is equal to ns, then P is equal to 1 kilowatt and h is equal to 1 meter. So substitute those values. P is equal to 1 kilowatt and h is equal to 1 meter and n is equal to ns in this expression 8. So if you substitute these values, P is equal to 1 kilowatt, h is equal to 1 meter, n is equal to ns in equation 8, what do you get? Left hand side it is 1. that is 1 kilowatt, that is equal to constant K into H is 1 raised to 5 by 2 divided by N is now, N has become Ns, specific speed. So what do you get now? 1 is equal to K divided by Ns square, because 1 raised to 5 by 2 is 1 itself. So 1 is equal to K divided by Ns square. In other words, K is equal to Ns square. So this is the value of the constant which we will get from the definition of the specific speed. So substitute the value of the constant K in equation number 8. So what do we get? P is equal to Ns square. See, instead of K, you are substituting Ns square. Ns square into H raised to 5 by 2 divided by N square. Now what do we require? We require this Ns. So transpose the other terms. So what do you get? N square into P divided by H raised to 5 by 2 is equal to, on the right hand side, now we have Ns square. So Ns square is equal to N square into P divided by H raised to 5 by 2. What is Ns? Is equal to square root of this whole group, N square into P divided by H raised to 5 by 2. When you take the square root of N square, it is N. When you take the square root of P, see, that is root of P itself, divided by H raised to 5 by 2, and you have to take the square root of that. What does it mean? H raised to 5 by 2 whole raised to 1 by 2. So that will be H raised to 5 by 4. So square root of H raised to 5 by 2 is H raised to 5 by 4. So Ns, the specific speed, is equal to N root of P divided by H raised to 5 by 4. Here N is the rotational speed of the turbine in RPM, P is the power in kilowatt, and H is the net head on which the turbine works in meters. And Ns is the specific speed. And this specific speed is dimensional. It has got a dimension, but it is not RPM. If you operate the various units of the terms in the right hand side, you will understand that. Now we will consider what is type number. See, the specific speed and type number of the turbine. What is the significance of type number in turbines? See, the specific speed Ns is equal to N root of P divided by H raised to 5 by 4, that has got dimensions. It is not the dimensionless form. But when the specific speed is expressed in dimensionless form, that is unitless form, then that will become type number. So the specific speed expressed in dimensionless form is called type number. In other words, the type number is the non-dimensional specific speed. So type number and specific speed, concept-wise they are the same. Only thing is that when you write the specific speed, it will be having the unit, it will be having the dimension, but when you write the type number, it is a unitless value. So type number is equal to N root of P by rho divided by GH whole raised to 5 by 4. So that means if you divide the power by the density of water, if it is a hydraulic turbine, and that P by rho is within the radical, and at the same time if you include in the denominator the gravitational acceleration g, and this, remember, this index 5 by 4 is applicable for both g as well as h. So type number is the non-dimensional or dimensionless form of the specific speed, and which can be obtained by making changes like this. What is that? Type number is equal to N root of P by rho divided by GH whole raised to 5 by 4, where rho is the density of water, that is 1000 kilogram per meter cube, and g is the gravitational acceleration, say 9.81 meter per second square. And when you operate this value, make sure that this n is in RPS, because you want to make it dimensionless. The significance of type number is exactly the same as that of the specific speed. Moreover, one definite advantage is that in engineering very often we use dimensionless ratios or dimensionless form of the quantities in engineering analysis, which will be quite convenient. Now we will solve a simple numerical problem from the previous KTU examination related to the specific speed of a turbine. The question is this: Kaplan turbine works under a head of 26.5 meters, the flow rate of water being 170 meter cube per second. The overall efficiency is 90%. The turbine speed is 150 rpm. Determine the power and the specific speed. Here the net head on which the turbine works, capital H, that is given 26.5 meters. The flow rate Q or the discharge is given as 170 meter cube per second. It is a huge discharge that is usually handled by axial flow turbines. Overall efficiency eta naught, that is given a 90%, that is equal to 0.9, and the rotational speed of the turbine runner in rpm denoted by capital N, that is 150 rpm. Since overall efficiency is given, we will be in a position to find out the shaft power. Overall efficiency is equal to shaft power by water power, that is P divided by rho Q GH. That is shaft power P is equal to overall efficiency into rho Q GH. That is 0.9, that is overall efficiency, 1000 kilogram per meter cube, that is the density of water, and the discharge Q 170 meter cube per second. G is the gravitational acceleration 9.81 meter per second squared, and the net head H 26.5 meters. If you take the product, you will get shaft power is equal to 3 crores 97 lakhs 74,645 watts. That is more than 39 million. So if you divide this quantity by 1000, you will get the shaft power in kilowatts. That is 39,774.645 kilowatts. Further, if you divide this by 1000 again, then you will get the shaft power in megawatts or million watts. That is 39.775 megawatts. That is the answer to the first part of the question. And now the specific speed. Specific speed is given by n suffix s is equal to n root of p divided by h raised to 5 by 4. We know that if you want to get the specific speed in SI units, then the shaft power must be substituted in kilowatts, and the rotational speed n in rpm and the head in meters, and therefore n root of p by h raised to 5 by 4, that is equal to 150 into square root of 39,774.645, that is the shaft power in kilowatts, that divided by 26.5 raised to 5 by 4. 26.5 meters is the net head. So you will get the specific speed ns in SI units 497.55. Of course, this has got a dimension, but it's not in rpm. Better to leave it like that. 497.55, that is the dimensional specific speed of the given turbine. See, this specific speed is between the range 250 and 860. So that rightly categorizes the turbine as an axial flow reaction turbine. So if the specific speed is between 250 and 860, that will be an axial flow reaction turbine, which of course in this case is Kaplan turbine.